Continue on Physical Chemistry, Chapter 18, Section 5 now. Now we're going to talk about the uncertainty principle. See the uncertainty handout. Now, electron diffraction shows that electrons can have wave-like properties. Neutron diffraction requires a nuclear reactor. So, V sub x means the x component of the velocity, or the velocity along the x-axis. And we're going to say that equals to 0. So, rho sub x, the momentum in the x-axis, or the momentum along the x-axis, that's going to be equal to mvx. Now let's say, what's the condition for the first diffraction minimum? So, looking at the diagram, you see you have segment dp minus ap, that's going to be equal to 1/2 lambda, the wavelength. That's going to be equal to cd. So cd has to be equal to 1/2 lambda for destructive interference, minimum intensity. So here's the graph we're talking about. Here's ACD, here's the angle theta. The difference between C and D is 1/2 lambda. Or here's another way showing 1/2 lambda is basically 180 degrees of the wave. Obviously the wavelength would be a full 360 degrees. We'll be using degrees instead of radians. We don't want to confuse our pi's. Okay, so D is going to be equal to the length from D to E. D is going to be a lot greater than W. So alpha is roughly equal to 0. Alpha is the angle. So angle ALD, or ACD, sorry, is going to be equal to 90 degrees. And angle PAC is going to be equal to angle ACP, which is going to be 90 degrees. And then angle BAC is going to be equal to angle ACD, which is roughly equal to 90 degrees. And angle ACD is equal to 90 degrees. Then angle PDE is going to be equal to angle DAC, which is equal to theta. Then angle ADC plus theta is going to be equal to 90 degrees. So theta equals 90 degrees minus angle ADC. Now sine theta is going to be equal to the length of DC, segment DC, divided by the length of segment AD. That's going to be equal to 1/2 lambda over 1/2 W, which is equal to lambda over W. So remember, lambda is the wavelength of the wave, and W is the width of the slit. So the first diffraction occurs at angle theta, or, well, the first diffraction minimum. Now the first diffraction minimum happens at both P and R. So here's X, here's our coming through this way, the slit's over here, we have angle theta, and this will be the momentum. So here's the momentum in X. So we have the momentum in X is rho sine X. Remember, rho is momentum. So the first diffraction minimum happens at the angle plus theta and at minus theta, if we're looking at, one-dimensional screen here. So see handout figure 65. So then we have the change in the momentum of X is going to be equal to rho sine theta minus a negative rho sine theta is equal to 2 rho sine theta. So remember, sine is an odd function, which means that minus sine theta is equal to minus sine theta. Cosine is an even function, so cosine of minus theta is just equal to cosine theta. So the change in the rho of x is the uncertainty in the rho sub x value. So we have the change in the rho sub x is equal to 2 rho lambda over W. So use de Broglie, we get lambda equals h over rho. So we have the change in rho sub x is equal to 2 rho h over rho W. The rho's cancel out, so we get 2h over W. So remember, rho is the total momentum. So we get the change in x is equal to W. Remember though, W has to be very, very narrow. It's the slit width. So now we get the change in rho of x is equal to 2h divided by the change in x. Remember, h is Planck's constant, which is a very small number. H is equal to 6.63 times 10 to the negative 34 joule seconds. Now there's an inverse relationship between the change in x and the change in the momentum of x. So the change in x times the change in the momentum of x is equal to 2h. And of course it depends on exactly how you do the diagram. So the change in the rho of x times the change in x is greater than or equal to h over 4 pi. Now you'll get different variations of this formula depending on how you derive it. Now, uncertainty in the momentum times the uncertainty in position is at least Planck's constant. Now we get the change in x times the change in the momentum in the x component of momentum is greater than or equal to h. So we get same thing for y and z. So before the slit, we have the momentum in x is 0 because the light is coming straight from the left. And then the change in x would be 0 because we know the light's going exactly through that one spot, the slit width. Then we have the change in the momentum of x is equal to 0, and the change in x is equal to w. Then we get, Bohr was fascinated with orbitals. So remember, planets have definite orbits. But an electron has a definite circular orbit would mean that the uncertainty or whatever, delta r is equal to 0. Which means then the momentum would be equal to infinity. And therefore the change in velocity is equal to infinity. Remember, r is radius, rho is momentum, and v is velocity. So if an electron goes in a circle, then delta rho is equal to 0. So the x component of the change in the momentum is equal to h over delta x, which is equal to h divided by 0, which means infinity. Can't divide by 0, but it'd actually be undefined. But anyway, so change in velocity would also be infinity. Now remember, angular momentum is mvr is equal to nh over 2 pi. Now, an S shell has no orbital angular momentum since L is equal to 0. We haven't talked about that yet. It'll come up. So here's an electron in an S shell. So now let's talk about Schrodinger's cat. So we have a radioactive detector here. And we have the cat over here. We have a hammer that's going to break the ampule with hydrogen cyanide gas in it. So if this detector finds a radioactive particle, it releases the hammer and releases hydrogen cyanide, kills the cat. But if this is a sealed container, we have no way to know whether the cat is alive or dead unless you actually open it up and look. It's not like there's a formula that will tell you when the radioactive particle is going to set off the radioactive detector and therefore the hammer, etc. So there is no way to know whether the cat is actually alive or dead. Now, according to wave theory, a particle can be two places at the same time. In this case, the cat is both alive and dead.